Hey, it's Tony from Adafruit, and this is a stream on MicroPython and analog inputs and outputs. So in the previous stream, which by the way, I'll put a link in the description below that goes to the previous stream I've done on digital inputs and outputs, and even just like what is MicroPython. So if you're new to MicroPython, check those links out when this is up on YouTube. But in a previous stream, I talked about digital inputs and outputs. So digital in the sense that it's either on or off. There's nothing in between. So it's either like a high logic level, like 3.3 volts, or off, like 0 volts, ground logic level. And so with that digital input and output, you can still do interesting things. Like you saw, you could look at a switch or a button and read if it's pressed or not. Or maybe like a door sensor that has a little magnetic sensor and a magnet. Lots of things like that you can do. Or even just turning an LED on or off. Or things that are more interesting like a relay. You can turn a relay on or off that controls something like maybe an appliance or something with a lot of power. And again, it all just comes down to it's digital inputs and outputs, so it's just an on or off signal. And in this stream, I wanted to look at analog inputs and outputs. So analog in the sense that it's not just on or off. It's not just a 0 volt or 3.3 volt or 5 volt signal. It's something in between. It could be any voltage actually, because voltages are continuous values. So you could have halfway in between on and off, 1.8 volts, or you could have a millionth of a thousandth of a volt above half, some very small value that you might not even be able to measure, but that's still a different value. It's an analog value in the sense that it can be any voltage value. And so in this video, we'll look at a couple different ways that you can deal with analog inputs and outputs in MicroPython. So you can do things like read analog values using an analog to digital converter that's built into a lot of chips. And you can also write analog values in the sense of like creating an output that you set to any voltage within a certain range, using different things like a digital to analog converter or what we call a PWM or pulse width modulation output. That's not exactly an analog output, but you can make it act kind of like that. And so I'll show you some interesting things we can do. So let's just kind of dive in. We'll get started here. Let's see, we'll go to the main view. So here's the main view, and it's not super interesting right now. Let me pull up this. So this is a guide that'll go along with this video, and it's basically all about analog inputs and outputs with MicroPython. And so I'll just kind of run through this, and I'll show two different kind of examples here. So the first is using an analog to digital converter to read analog values, like read a voltage. And then the second is pulse width modulation, which you can use to dim an LED, for example. So it's a way to, I would say, simulate, or you really can create actual analog voltage values with it. It's just, I'll show you, it's not necessarily an analog thing. We're actually using some digital on and off technology for this. So we'll just kind of dive in and get started with this and go through it. So the first thing that I wanted to show, oh, and also in the upper right hand corner here, so there's actually a lot going on. There's some stuff here that you don't see. There's a little logic analyzer here that we're going to be playing with here. But right here, this is the main attraction. This is the ESP8266 Feather Huzzah board. It's running MicroPython. Again, check out the What is MicroPython guide that I have. I'll put a link to. If you don't know anything about MicroPython, start there. That links to how to load MicroPython onto a board, what boards support MicroPython, all types of stuff like that. So start there first. This is more for if you're a little more experienced. But that's what we've got here. And then there's a potentiometer connected to it and an LED. And this LED is actually connected exactly the same way as all the other videos I've done, where I just have an LED connected with a little resistor right here down to ground. So you can turn it on or off, but I'll show you, we can actually dim it later. And the potentiometer is interesting, and we'll talk about that in a second here. But then this is also hooked up to, I just have a multimeter here that's reading the output of the potentiometer, because the potentiometer is a variable resistor. So when you turn this little knob on the top here, this is a nice little breadboard friendly one, so you can just turn the knob, twist it like that. It's actually changing the resistance that's output, or not necessarily output, but it changes the resistance of it on this middle pin. And if you send a voltage through that, you can actually change that voltage based on how the resistance changes. So we'll see what that voltage is with the multimeter. And then the cool thing is, as we'll talk about in a second here, that voltage can be fed into the analog to digital converter that's built into the ESP8266. And we'll see how it can convert that voltage into a number that your program can deal with. Because it's a little hard, even though this is high-level Python code, you don't really have a concept of read this voltage and give me back, 1.8725 volts or whatever the value is. You can compute that, but that's not necessarily how the hardware works. So at a lower level, the analog to digital converter is actually just looking at, more of just a fixed number, some value that's maybe like a 10-bit number or 12-bit number, like that. So we'll kind of dive in here and look at this. So let's look at the analog to digital converter example. So I just talk a little bit at the top about how, what is an analog to digital converter. So think of it as just a way to read voltage from a microcontroller. So a lot of things like the ESP8266 has an analog to digital converter built in. Other boards like the Pi board, this has some analog to digital converters built into it. I think it has 3 of them, I want to say. Yeah, I actually have a list right here. Then there's this one, the YPi. So this has 4 analog to digital converters. And so the important thing though to realize with analog to digital converters, none of them are perfect. There are limits to all of them. So there's a concept of like the accuracy. So, how accurate of a voltage reading can you get? And so the ESP8266 has a 10-bit accuracy, which just means that it can read a 10-bit range of values, which means from 0 to 1023. So it can read 1024 unique voltage values over some range of voltages. So that's the other important aspect of an analog to digital converter, is there's a maximum voltage that you can send into it, which is kind of the range of what are the values that it can read. And for the ESP8266, it's actually just 1 volt. It's fixed. So you really shouldn't go above that 1 volt. You can damage the board. In a lot of cases, you really need to be careful about that. So again, it's different between all of the boards. So like the Pi board has a little bit nicer ADC, 12-bit accuracy. So that gives you values between 0 and 4095, or like 4096 different values. If you're ever curious, you can figure these limits out. Just take 2 to the power of whatever number of bits. So like 2 to the 10 minus 1. That'll give you the maximum value that you can have with a 10-bit number. So same thing for 12 bits. But anyway, so you can see it's a little bit more accurate and it can have a higher voltage range here. So again, with analog digital converters, there's no perfect one, at least as far as I'm aware of. Or if there is one, it's going to cost you a lot of money. There's nothing that just takes in any voltage and gives you perfect accuracy. So there are trade-offs here you have to kind of worry about. And again, when you're dealing with analog signals like this, you sometimes need to think about like how to filter those signals, maybe how to amplify them. If you're dealing with like a sensor, for example, that's outputting just a very small voltage, if your analog to digital converter expects a value in the range of like 0 to 1 volts, and your sensor is only outputting like 1/10 of a volt, you're not going to get a lot of values out of that because your range is really small. So you might need to amplify it up using like an op amp or an instrument amplifier. Lots of different techniques and things you can look at for that. Some analog to digital converters have like a programmable gain where they can have an amplifier built into them. So lots of cool stuff to think about. But again, it's, you really need to think about getting a good signal into your analog to digital converter before you really try and fix things in software. Get a good signal and then maybe see what you can do with software. And the other thing I should mention with MicroPython specifically, the analog to digital converter interface is a little bit different between all the different boards. So I call out here, basically check your board's documentation, and I put links explicitly to these documents. Like the Pi board, for example, if you look at the documentation here, it uses a slightly different class, this PYB, the Pi board class, or module rather, compared to like the ESP8266. It uses the machine module, so you import from the machine module. So little differences. I think over time they're going to try to unify this with MicroPython, but wherever I see differences, I try to call them out in the guide here. And the YPi is also a little bit different, so check out the documentation for your board. But the basic ideas, again, are all the same here. You've got an analog voltage value, you can read it with the analog to digital converter and get a numeric value back, so that now your program can reason about, what's connected to that analog to digital converter. So in this case, it could just be like a simple little potentiometer that's just a toy example, but it could be something else. It could be, an analog sensor like a thermistor or a light sensor, a force sensitive resistor, any kind of thing that changes its resistance could also change a voltage, and then if you've got a changing voltage, you can feed that into an analog to digital converter and read what that value is. So for this example, we're just hooking up this potentiometer so that as I change the resistance by turning the knob here, we'll be able to read that as a different value on the analog to digital converter. Now be really careful when you follow this. Make sure to build this circuit exactly as I show it here, because again, the ESP8266 analog to digital converter has a limit of 1 volt that you can pass in, like a maximum value of 1 volt. And the issue is, so, if I want to send some voltage through this little potentiometer and then get an output voltage, if I send in 3.3 volts, and if I twist it all the way to one extreme where it's basically giving me that full input voltage on the output, that could damage the analog to digital converter. It wouldn't be very happy to have 3.3 volts going into it. So what I do is I create a voltage divider here, which is you just put 2 resistors into a certain little configuration here, and that can basically cut your voltage down. So I take that 3.3 volts and I cut it down to, with the 2 resistors I show here, a 10 kilo ohm and a 47 kilo ohm resistor, this will cut 3.3 volts down to about half a volt, so like a little bit higher than half a volt. So it's not the full range of 0 to 1 volts, but I did this because I wanted to use 2 common resistors that are in this nifty little Parts Pal pack. So if you pick up the Parts Pal, I'm trying to make all these tutorials use the parts in that. So that's kind of easy. If you do want to get that full range of 0 to 1 volts, use a 22 kilo ohm resistor. That's another common one, so just pick up one of those and use it in place of the 47 kilo ohm right here. But again, be sure to do this configuration like I show it here, and make sure to get the resistors correct here. If you swap these, you'll actually send more voltage in and could damage it. So, and again, like I said, so this just comes back to when you're dealing with these analog signals and analog to digital converters, you're probably going to have to do some modifications to your signal, like amplify it, or maybe you're like cutting down the voltage here. But anyway, so the way it works then, so I take that 3.3 volts, I cut it down to about half a volt in this configuration. I send it into one end of the potentiometer, and then on the other end of the potentiometer, it's connected to ground. And inside of here is just a resistor. So, just think of this as a resistor. So it's just, there's some current that just passes straight down to ground. It's not really doing anything. But when you twist this knob, it changes the resistance. And there's a middle pin here, and this middle pin, the wiper I believe it's called, so the wiper is kind of connected to the point where it's changing that resistance. And so the way this is configured, it's actually a voltage divider inside of here, and so this output voltage, or this output pin, will change its voltage based on how you twist the knob, how you change the resistance inside of there. I think it'll make a little more sense when we start reading the values, and you can kind of intuitively see as the voltage changes, the values you get back change, and as you twist the knob, you can see how the voltage changes here. But so ultimately, all that this circuit does is just output a voltage that changes as I twist this knob, and it feeds it into the ADC input, the analog to digital converter input on the ESP8266. So that's all that I have wired up here, and let's just kind of dive into the code and we'll just see what we need to do to read the values from this. So actually I'll turn on my multimeter maybe before we even do anything here. So we'll just put it into voltage mode here, and you can see it's reading about 208 milliamps or millivolts right now. And so I'm going to twist the knob all the way to the left. So now it's reading about 318 millivolts, so about 0.3 volts. And then if I twist it all the way to the right over here, now you can see we're pretty close to 0 volts. So, like maybe, like 1 millivolt basically. So, pretty much ground, or it looks like, we're on ground right now. And then if I go halfway in between here, we'll see we get a value of about 150. So this is kind of nice. And it's a nice linear response from 330 or so millivolts on one extreme all the way down to the other extreme to 0 millivolts or ground. And then this middle pin is kind of what I'm reading the voltage from here, and that's also fed into the analog to digital converter. So let's connect to the REPL on the board, and let's start using the analog to digital converter. So to use this on the ESP8266, and again, this is a little bit different for each of the boards. So I call out, like on the Pi board, there's a different module that you need to import. For the YPi, there's a slightly different syntax for this. So, just be aware it's a little bit different. But let's import the machine module. And then from here, we can create an analog to digital converter object. So we can basically assign a variable to an instance of this ADC class. Now, this is kind of boilerplate in that the ESP8266 only has one analog to digital converter, and it only has one channel. So it's not really fancy. You just have one. So when you create this ADC object, you just have to pass 0 in as the instance here. It doesn't assume this. You just say, okay, I want the only analog to digital converter, or the first one that's on this board. This gives you an ADC object. And then at this point, you can actually just call adc.read, and this will give you back a number. Now for the other boards, it is a little bit different. The other boards actually have a concept of multiple channels, which just means that you might have one physical analog to digital converter that has like multiple input channels, and you can read each of those individually. And so there's a little bit more syntax, but again, like I said, go to the documentation for your board. You just, in some cases, you have to call a channel function, and then and you tell it which channel you want to read, and that'll give you back an object, a pin object or a channel object that you can call this read function against, except on the YPi where it's called value instead of read. So again, I call out a little bit of difference here, but it's all the same basic idea. Okay, so I'm going to call this function again, and you can see every time I call this, I get pretty much the same value. I'm getting like 171. Now I'm going to twist the knob maybe all the way to the right, and so you can see the voltage here just dropped down to like almost 0, so almost nothing. And now you see we're getting a pretty small value 5, 6, tiny little value. Now you might notice also like the value does kind of change a little bit. So it went from 5 to 6 and then back down to 5, and something wrong. But that's just kind of normal. Like there's some noise as far as the input kind of reference voltage. If that fluctuates a little bit, that can change the values that you get. So again, there's with analog values, kind of like in programming, a lot of people say with floating point, you never do like an equal check. Like, is this floating point value equal to like 1.25? Because there's always this little margin of error that you have. So you want to look at some small little range of values, like is it equal to 1.25 plus or minus a tenth of a percent or something. So same kind of thing with analog values. There's a little bit of wiggle room here sometimes where the signals might change, there might be some noise that you pick up. So just be aware that it is normal to see these values fluctuate a little bit. If you see totally random fluctuations, like if I keep calling this and if I get like 5, 6, and then like 100, and then 30, and then 5 again, and then 100, that's a little weird. Something is wrong. So make sure like your wiring is okay. You should get pretty similar values, but they might change. And if this is a problem, one thing you can do, you can actually just call read multiple times and just average out those values. And that'll smooth it out and give you a value that doesn't change as quickly. So something a little more stable. Real nice kind of easy way if you're maybe trying to change the behavior of something based on like the position of a potentiometer. Okay, so let's change it all the way to the other extreme now. So we're going to get to, a voltage of like 319 or so millivolts. Now let's call ADC read. And so cool. So now you see we get a value that's like 340-ish, 338. So it's a higher value here. And again, it's, kind of like a linear change. And if I put this back in the middle roughly, we should see a value, yeah, like 178 or so, and like 164 milliamps here. Now the value that comes back from adc.read, you might wonder, okay, what is the range of values here? And again, this comes back to the accuracy of the ADC. So on the ESP8266, it's 10-bit accuracy. So that means that the values you can get back will range from 0 to 1023. And you would get a value of 1023 if you had 1 volt or even higher than 1 volt. But again, be careful, don't send more than 1 volt in. If you had 1 volt going into the analog to digital converter input, that would give you the maximum value of 1023. And if you have 0 volts, like a ground level going into it, then you'll get the minimum value of 0. And if you have half a volt exactly in between that range of 0 to 1 volts, you should get a value of about 512, which is halfway in between 0 and 1023. So that's really all that happens with the analog to digital converter. It's just reading that voltage value, looking at where it falls within the range that it's kind of configured to look at, so like 0 to 1 volts here, and then just mapping that to a value that falls within the accuracy that it has. So with 10-bit accuracy, you get a value from like 0 to 1023. So, this is an easy way I can read this potentiometer. So if I, twist the potentiometer down, I'm going to get a lower value. If I twist it back up, I'll get a higher value like this. And I could do cool things with this. I could maybe control like the intensity of an LED or something like that with it. So again, that's all I wanted to show. And I will show just real quickly, if you want to get a higher range, this is a little, this is a 22 kilo ohm resistor. So I'm going to swap out the 47 kilo ohm resistor, and we'll just put in this smaller one. This changes the voltage divider, and so now I should have pretty much the full 1 volt input to the potentiometer, and we should see actually the multimeter show us that difference too. Okay, so I just plugged it in, and so now you can see we're at about half a volt right now, and if I crank it up a little bit more, we're a little bit higher, so about like 600 milliamps or so. It's about double the voltage that we had before. So it's not the full 1 volt, just because the divider it's not exactly cutting it down to 1 volt. But this is good, at least I see. I'm only sending 600 milliamps, so like 0.6 volts in, so it's under 1 volt, so I'm not going to damage the ESP8266. Now if I call adc.read, notice I'm getting higher values, so I'm getting like 651 right here, and it's actually pretty close to the voltage value in millivolts, because that range of 1023 versus 1,000 millivolts in 1 volt, they're pretty close. There's a little bit of error there, but this seems like I'm getting the right values. And then if I crank it down like to halfway, I should see around like 300 or so, yeah, like 326. And then if I go all the way down to 0, again, we should see, yeah, we get down to about 5. And I think this is just because, there's always going to be a little bit of resistance inside that potentiometer, so you're never going to get perfectly down to ground with it. But that's all there is to reading analog stuff. It's as simple as just connecting an analog to digital converter. Again, be aware and think about what's the accuracy, like how many bits do you have with this, and then what's the input voltage range. And every chip is different. You can actually get dedicated analog to digital converters that are really advanced. Like I said, you can get very accurate, like maybe 24-bit accuracy. You're going to pay a lot for that probably. You can get really fast analog to digital converters. Like there's a whole range of things you can do. But just use what's on the board in a lot of cases. You can do a lot of cool stuff with this. Like one really nice thing that a lot of people will do in a project is if it's a battery powered project and you're curious what your battery level is, you can actually take like your battery voltage and just feed that into an analog to digital converter and then read that in your program to see, okay, my battery voltage is like 3.7 volts, so it's like fully charged up, or maybe it's fallen down to like 1.8 volts and now it's out. So it's kind of nice that you can do simple things with that. Okay, so let's go now to the next thing in the guide. So the digital to analog converter. So I don't really go into a lot of detail for this. So, I just talked about analog to digital converter. That's how you read an analog value. Now, digital analog converter is the opposite. So basically, you can generate a voltage value. So by feeding in a number, just like using an analog to digital converter. So there's like a 10-bit, 12-bit, you have some number of bits that you support for your DAC. You can feed in some number that says, okay, here's a value of 1023, and this should be maximum voltage output. Or here's a value of 512, this should be half the voltage output. And the cool thing is, you can manipulate this voltage value over time. So you might have like a signal, like music, for example, is just a bunch of digital samples, a bunch of digital values that you feed into a digital to analog converter. And then that gets sent into an amplifier, and then that gets sent to a speaker. So the speaker can make music, because the speaker can't just play those digital samples directly. It needs a signal that moves up and down like in a sine wave that's pushing that speaker forwards and backwards. And so the way that you do that is you use this digital analog converter to take those raw samples and convert them into a voltage that changes over time. Now, it's not super common for for chips to have a digital to analog converter. At least the ESP8266 doesn't have one, unfortunately. The Pi board does have one built into it, so there is a DAC on board this. I think it's a 12-bit DAC. So I didn't really get into it here because I'm mostly focusing on the ESP8266 right now. But if you are curious and you do have a Pi board, check out the documentation. It looks like it's pretty easy to use. You really just call a few functions here, and there's a write function. So, before we saw that there's a read function and that returns you a value between like 0 and 1023. The write function takes in a value, and then we'll just set the voltage for the DAC for that. So that's one nice thing, that you can use a DAC when you want to generate voltage values. Maybe you want to control like the intensity of something that's voltage controlled. Another thing you can do, though, is something called pulse width modulation, or PWM. And so this is kind of interesting. This is a way, I would say, you can generate voltage values with this, but you're not going to generate them directly out of the pin. You have to do a little bit of filtering to it. And the way that this works is that you can make a digital signal, so it's either on or it's off. It's never in between. You have a digital signal that turns on and off very quickly at some frequency. And if you're talking to a device that can't really process it at that frequency. Or, think of your eyes. You can only see things that happen so quickly. I don't know what the exact value is, but we probably can't make out something that changes more than like 100 times a second. So imagine if you have a signal that's changing like 1,000 times a second, much faster than a human eye can see. Like it's turning on and it's turning off 1,000 times a second. When we see that, when we look at that LED, we're just going to see some constant value. It's going to be on or it's going to be off, or maybe it's halfway in between on or off. Like our eyes are kind of averaging out that on and off signal so that we just see kind of what the average value is for it. And then the cool thing with PWM is the pulse width, the modulation part is you can change how long is that signal on versus off. So if it's turned on for more than it's turned off, then you're going to see like a higher average value. Or if it's turned off more than it's turned on, you'll see a lower average value. And a really good way to visualize that is to connect an output to an LED like this and then send it a PWM signal that you change what's called the duty cycle, or the percent of time that it's on versus off. So if you have a high duty cycle, like 100% on, it's always going to be turned on. Or if you have like 50% duty cycle, so halfway in between, you should see a signal that's on for just as long as it's off. And then you could go even lower, and in all of those cases though, it's going to change the brightness of that LED because it's going to be turned on for a longer amount of time with a higher duty cycle. So we'll see more of the light that comes from that LED. Like we'll see it turned on more often than it's turned off in this case. So we'll go through and we'll just show a quick example of PWM. Again, this is another case where MicroPython, each board is a little bit different. The ESP8266 is actually pretty simple. It has this little PWM interface. For the Pi board and the YPi, they use this lower level timer interface. Well, I guess my multimeter is mad at it wants to turn off here, so we'll keep it happy. I guess I don't really need it anymore. But anyways, so like I said, the Pi board and YPi are a little different. They use this timer interface. It's not much more complex. So again, look at the documentation here, and it's really just you have to create this timer object, and you have to manipulate like the duty cycle in a slightly different way. But again, the basic ideas are all the same that I'm going to go through here. There's a frequency that the PWM signal will change at, and then there's a duty cycle, which is kind of the percent of time that it's on versus off. And we'll actually see, so I have connected up here, this is the Salier Logic Pro 8. Really nice little logic analyzer, and actually I'll put a link to these in the description below. This one's a little bit advanced. Think of it almost like a little oscilloscope. It can actually read analog signals. The Pro versions can do that. So it's kind of handy, and so I have it hooked up to this LED, one of the pins that's driving the LED. So we'll actually be able to look at this PWM signal and see what it looks like. That'll be kind of neat. Oh, and by the way, if you like this multimeter, this is the X-Tech, the EX330. Real nice little rugged multimeter. It's a good one. If you're looking for a nice multimeter, grab this one. I'll put links in the description below if you're curious to check these out. Okay, so let's get started here. So the circuit for this is just the LED wired up with a resistor down to ground, exactly the same as I've shown for like digital inputs and outputs. It's really just the code that we're going to change here. So let's go back to our Pi board, our ESP8266 and the REPL, and let's get started here. So you need to import the machine module again. And then we need to create an instance of this PWM class, and this takes in a pin object that you can also just construct right here. So this is just how you say, okay, use this GPIO pin as a PWM output. And also be aware that pin 16 on the ESP8266 doesn't support PWM output. So some of the pins sometimes don't support it, but pin 15 is okay. So let's do that. We'll do PWM equals machine.pwm, and we pass in the pin, and you don't pass in the number, you have to pass in the pin object for this. So we construct that. And okay, so now we've got a PWM object, and there are a couple things you can do. So you can set the frequency of the PWM signal. So this is how often it goes from on to off, how many times a second it does that in hertz. And in this case, for lighting an LED, like I said, our eyes can't really make out like more than, I'm sure, 100 times a second or so. So I'm just going to set the frequency pretty low to 60 times a second. So you can just call the frequency function, to set the frequency of the PWM output. And you can actually just call that function with no parameter and it'll return back the value. So if you're kind of curious like what it was set at, you can get it back. One thing to realize though is there's only one frequency that's global to all of the PWM outputs. So you can have multiple PWM outputs. I could make another one for, you know, different pins, but if I change the frequency on one, it will change the frequency for all of them, which usually isn't a problem because, you know, maybe you're talking to servos or LEDs or things that all could probably work with the same frequency, but just something to be aware of that you don't have complete control over that. Okay, so now we've set the frequency. So the other thing to change is the duty cycle. So there's the pwm.duty function. And this one, it takes in a value, it takes in a 10-bit value on the ESP8266. So again, just like with the analog to digital converter, we read 10-bit values. With this, think of it like you're writing a 10-bit value. So a value of 1023 here just means that it will be turned on 100% of the time. You know, this is the maximum value. So if I set pwm.duty to 1023, let's see what happens. Hey, check this out. The LED just turned on and it looks pretty bright. Like, you know, it looks like this is full brightness. But let's try changing the duty cycle again. So let's set it down to 0, and now we can see it turns off. It's like, you know, there's no, the signal is just never turned on with a duty cycle of 0 or 0%. And let's go halfway in between, so 512. So in this case, it turns on. Now it's probably a little hard to see because the camera is going to do like auto exposure, so you know it's a little bit less bright. Let's go down to like a smaller value, like how about 25, and see if you know. Okay, so you can tell it's definitely noticeably dim in this case. You know, it's turned on, but just barely turned on. And then if I go up to like maybe 900, something a lot higher, it gets pretty bright. And then maybe let's go back to like the full value, 1023. So it's, you can't even tell, but it's maybe a teeny bit brighter in that case. So okay, let's go back to the halfway. So PWM duty 512. Okay, so let's look at what this duty cycle thing means. So I'm actually gonna open up this software. So this is Salier's software. So again, like I mentioned, I have a little logic analyzer hooked up, but I'm using it in its analog input mode. So this is the cool thing about the, I think it's only the Pro analyzers, but maybe the lower ones also have it too. So I have it configured, it's doing analog inputs. I could honestly you could just use a normal logic analyzer for this because, you know, this is just an on and off signal. It's a digital signal, so it's perfectly fine, but hey, we'll get fancy and we'll do the analog one. You know, hey, I got the Pro version, I'm gonna use those Pro features, darn it. Now the sample rate, I'm only gonna sample it 125,000 times per second. I can go up to 50 million if I want, but I don't need to, just because I've got all of my cameras going into the same USB bus as this thing, and this is USB 3.0, and you can use a lot of bandwidth with the 50 million samples per second. You turn on a bunch of channels. So, you know, generally you want to set your sample rate to, you know, whatever value makes sense. Where it makes sense usually means it needs to be at least double your frequency. So, you know, at least 120 times a second. But I go a lot higher because, you know, you got to deal with the Nyquist limit when you're sampling signals. I'm just going to grab a second of data because, you know, it doesn't really matter. We're not like trying to catch some instant in time. We don't need to trigger off of anything for this. So, okay, so that's what we're going to do. Let's just grab a sample here and see what's going on. So you can see here's the signal, and you know, I can zoom out, and then maybe if I zoom back in, you can see it's it looks like a square wave. Like it's just, you know, it's on and it's off down here. So like up here we're up at like 3.2 volts, so you know that's turning the LED on, and then down here we're down at like, you know, 0 volts or so, so basically down to ground. And you know, you can see there's like a little bit of distortion here, like it's, you know, you can never change perfectly, so there's going to be a little bit of ringing around here. But let's see what the frequency is for this. So if I grab this little marker and we'll put it like right when it jumps up to a high value, and then we'll grab this frequency or this marker here and we'll put it right where it jumps up again to the next value. So we can look at the range in between here where it's turned on and it's turned off inside of here. So we can see this is about 16.6 milliseconds or so of time that elapsed in between here. So if I look at a calculator here, if we do 1 divided by 0. How about 16.6? So basically just 1 over the number of milliseconds, the number of seconds. And then this will give me a value of 60.24. So this is the frequency in hertz. So basically this signal is changing 60 times a second. Or, you know, we see this on-off signal. It has a period of 60 times a second. which makes sense because notice I set the frequency here to 60 times a second. So let's just see, let's try if I set the frequency to double that, like 120 times a second, how this changes. So I'll grab another batch of samples here. Now it doesn't look any different, like it's still an on-off signal here, but let's see what the timing is. So we'll go and we'll grab one of these. And so now we see, I'm pretty close, but we're basically half. So we're 8 milliseconds now for this whole thing. So if I do 1 divided by 0.0084, how about, we get pretty darn close to 120 times a second. So that's cool. So you can see, like, you know, and that's all that this signal is doing. It's just going on, off, 120 times a second, over and over and over. Now, the other cool thing to see is that duty cycle, like I was mentioning. So, you know, if I just look at one little period here of it being on and off, you can see it's pretty much like halfway in between it goes from on to off, which makes sense because I set my duty cycle to 512, which is like just about exactly halfway between 0 and 1023. So that just means it's going to be turned on for half the time and turned off for half the time. And we can really double check if I move this marker over. We can see that, you know, right here it's about 4 milliseconds, and then one full period here is going to be, you know, 8 milliseconds or so. So let's change the duty cycle and see what happens here. So if I set the duty cycle, you know, let's set it to full. Let's go, you know, let's go big. We'll go fully on, and let's grab a little set of samples here. And now this doesn't look as interesting. You know, it's all the same value, and you can actually see this is going to be, you know, right around like 3.2 volts. So this makes sense. This is good. This is what we expect to see because I told it with this pwm.duty call, you know, set the duty cycle to 100%. You were just always turned on. And so we see exactly that here. It's always turned on. There might be like a tiny period where it turns off or something. It depends on the PWM hardware sometimes. And, you know, I'm only sampling 125,000 times a second. So, you know, it might not be perfect. But it's, for all intents and purposes, it is turned on all of the time. And then let's see. I'm sure you can guess what will happen if I do a 0 duty cycle. And then we measure this. Then we should see that, again, it's a straight line, but this time we're pretty much at 0 volts. So, you know, we're turned off or we're down at ground. And then if I set this to like maybe 100, so a small value here, let's grab, and you can see the LED is turned on, you know, kind of dimly in this case. Now I kind of have to zoom out if I remember correctly. Yeah, there we go. So we can start to see some of these. Okay, so let's look at one of these signals now. So I'll see if I can zoom in and move over. So again, you know, we want to look at the on-off part of this. So, you know, this is one period here. So let's put the marker where it goes on, and then we'll put the second marker where it goes on again. So again, about 8 milliseconds of time. So this is 120 times a second that we're seeing this. But now we're only turned on for a real small period here. Like, let's actually see what this is. So we're turned on for, you know, 0.7 or 0.8 milliseconds here. So almost like just maybe 1 millisecond out of 8 milliseconds total that we have here. And that's because, you know, we set that duty cycle to a value that's like, you know, just about 10% or so of its range. And so that kind of makes sense. You know, you can see here, we're turned on for about 10% of the time. So let's flip this around. Let's go to like 900 instead of 100. And so now we see, you know, LED gets brighter, and if I grab a new set of samples here and kind of zoom out, you know, now the signal looks a little bit different. And so let's see, we'll zoom in here and see if we can get a full waveform. So, okay, so let's grab, you know, a complete on-off signal again. So we'll start there, and then we'll end it right around here. And again, no big surprise, 8 milliseconds total, so 120 times a second. But now, you know, notice it's turned on pretty much 90% of the time and then turned off for that last little 10%. And you see that visually with your eyes, like it's a little bit less bright than if I went to that full brightness here. So that's all that's happening with this PWM output. You know, this is a digital signal. This is on and off. You don't see like a halfway voltage value in between here. But this can work to, you know, kind of simulate, I would say, analog outputs in the sense that, you know, if you're talking to a device like an LED that you're looking at and you know, your eye can't really tell that on and off because it's just averaging it out, then this could work pretty well. You can actually put a little filter in front of or after a PWM output, a low pass filter that will basically say, okay, average out this fast changing signal. And so that's kind of one way that you can take a PWM output and actually get a voltage value out of it that you might feed into something else. But like a lot of devices, you know, some of them can deal with these PWM outputs. Like a servo, for example, needs a PWM output that turns on and off quickly to move it to different positions. So, you know, it kind of comes down to just look at what you're dealing with and you know, can't take a PWM output like this. And think of the PWM output kind of like an analog output where you can control the duty cycle to control basically the voltage in some ways, or, you know, the intensity of that value. And then the frequency is also another important kind of variable that you need to worry about because, you know, the frequency that you want to set kind of comes down to what's the device you have this connected to. You know, if it's a device that can understand really fast changing signals, you're going to need to set a really high frequency in order to give it some value that it just sees as an average value for this. Okay, so that's it. I think that's all I wanted to cover in this stream was just how to do the PWM things. Oh, and I show a little bit more of an example here. Basically, you know, you can animate things. So if I put in this code here, then it will animate the LED. And I won't do it right now. We're running a little bit short on time. And again, the multimeter's mad at me, so we'll turn it off. But you know, this is really handy using this PWM output. You can dim an LED, and if you can dim an LED, then you can like animate it. So just, you know, ramp it up and down. So this code here, and I explain in the guide, you know, I just have a little for loop. Oops, I want to go back to this. You know, I have a little for loop that just goes through a range of duty cycle values and sets the duty cycle, and then just delays for a small period. So you ramp up from 0 to 1023 with this first part of the loop. And then this second part, you ramp down from 1023, like, you know, changing with a step size of -1. So the range function in Python is super handy. You know, normally if you just give it a value, it's going to go from 0 up to that value, but it doesn't include that value. In this syntax down here, you can tell the range function, okay, here's my starting value, so start at 1023. Here's my ending value of -1. So it's not going to give you that ending value. It's going to go up to the ending value, but not include it. And then here's my step size, or how I should change every iteration. And so the step size of -1 just means start from 1023 and subtract 1 with each loop iteration. So that's kind of, you know, if you're coming from the C and C++ or the Arduino world, you're usually used to like a for loop, you know, where you create an I variable and you explicitly subtract 1 from it. In Python, a little bit different. You use the range function, you give it a start, a stop, and a step size here. And the cool thing is, like, you could start from a positive value, end at an even higher value, and have, like, you know, larger step sizes and things. So you can go pretty crazy with it. But again, you can use that to drive a PWM output and, you know, control an LED, like dim it, you know, make it bright, make it pulse, fade, do all kinds of cool animations and things with it. So, okay, so if folks have questions, maybe throw them into the chat and we'll see if we can get to them. Let's see. Okay, yes, someone's mentioning, yeah, the ADS 1115 is a real nice analog to digital converter. Yeah, it's one that we have in the shop. It's an external analog to digital converter, so you'll have to connect it to your chip. And hopefully in the next few videos, I'm going to be looking at how to talk to SPI and I2C devices. So I can't remember which one. Most ADCs are SPI devices, I want to say, just because usually they're sending data really quickly. So in that case, you know, you'll have to kind of implement the protocol that it has. So there's usually, you're like reading a register from the ADC that has the sample values. But yeah, that'll probably be an example that I do in the future of looking at an external analog to digital converter. And the ADS 1115 is a nice one. It has like a programmable gain. So if you're looking at a small signal, like if you have a load cell, which is what you use to measure weight, usually you get like a really small voltage out of that, and you need to amplify it a lot to get it into that range that your analog to digital converter uses for this. So let's see, what else is in here? Yeah, there are lots of, yeah, the MCP 4725, that's another one that's got some, I guess it's a DAC. Oh, interesting. So yeah, that's kind of a cool thing for that. Let's see. So yes, folks were mentioning, yeah, the frequency is shared. So again, and just in general, whenever you're dealing with the hardware in MicroPython, Some of these hardware APIs are changing a little bit, so always check your board's documentation, like I mentioned, and in all the guides I try to link to it and maybe call out some of the differences, because yeah, like on the ESP, it has a frequency that's shared between all the PWM outputs, but on other boards you might have, because you're using explicit timers, you could have complete control over like a separate frequency for each of the different PWM outputs. So things are going to be a little bit different compared to different boards for that. So someone mentioned, yeah, you might use a buzzer or something with a PWM output. Yeah, you could totally do that, because music and sound is just a value kind of like this LED. It's a continually changing on and off signal. Now you're not going to get a pretty sound if you fed something like this. This is called a square wave because it looks like a square. It's just completely on, completely off. So if you fed this into a speaker, you're basically just instantly pushing that speaker from like fully extended to completely extended in the opposite direction, which you can actually damage speakers. So be careful sending square waves into them. Usually you send like a sine wave, nice smoothly changing value into it, and that's why usually you want to use like an explicit digital to analog converter that lets you get a little bit nicer control over those voltages. But you probably could, in theory, put like a low pass filter in front of after a PWM output, and then throw that into an amplifier and a speaker and get sound out of it. So lots of cool things. But if you just want to make like a buzz sound, you could feed a PWM output into a buzzer, like a piezo buzzer, and that'll probably give you what you want. You can, and if you change that frequency, you can change the frequency that you hear with your ears. So like the duty cycle, you'd keep it like maybe 50% so that it's just on and off half of the time, but then adjust that frequency to change how you hear that. So fun thing to try maybe later with this. So cool. I think that was it. So that was all the questions. We'll jump back to the main kind of headshot here. So yeah, that was it. This was analog inputs and outputs with MicroPython. Tony from Adafruit. So if you like this video, check out youtube.com/Adafruit. You can see this video and all kinds of other fun project videos that we put up there. Pretty much almost a video every day, sometimes more than that. So check that out. Then check out twitch.tv/Adafruit, and that's where I like to stream these things live. So I do a couple live streams each week and look at different things. All last month I did MicroPython, kind of did all the basics. I think I'm going to keep going with maybe another month of MicroPython because I want to start getting into more of the hardware stuff. So we just looked at digital inputs and outputs with the last video, this video, analog inputs and outputs. And like I said, I think the next two videos, I think I'm going to do one on SPI, the SPI kind of serial interface, and then I2C, which is another serial interface for talking to different chips. So then things will start to get a little interesting because now we're talking to other chips and maybe starting to do things like control little like OLED displays, or maybe talk to like real nice temperature sensors and stuff like that. So look forward to those videos. I like to do a video on Mondays and on Fridays. This week is a little weird because we had the holiday Monday, so I'm doing this on Tuesdays. And then this Friday, there won't be a video. I'm going to try to do a video early Thursday. I'm heading out of town, so I won't be around. But if you're down at the Portland Mini Maker Fair, I'll be down there this weekend. And then also the Rose City Comic Con and also the XOXO Festival. So it's going to be a busy weekend in Portland, but I'll be around down there. So yeah, like I said, if you like these videos, click the like button, the subscribe button, comment, let us know that this is cool and useful info, and we'll keep doing this. So until then, this is Tony from Adafruit. I'll see you guys later.